Okay, so welcome to the third lecture on module 9. That is, we discussed in the last class that we are looking at in details about the formal algorithm for automatic test pattern generation by sensitize, propagation and justify approach, that is the D algorithm. And on that we said that we will be actually having two lectures in covering the formal algorithm. So, in the last lecture we have discussed about the definitions and some of the procedures, okay, that would be required for this D algorithm. And then in today's class we will be illustrating D algorithm in detail. That is, this D algorithm we will formally discuss, and with the help of examples we will try to illustrate this flow of the algorithm. Okay, so, what is the input and the output of the D algorithm? So, the circuit netlist with one stacked fault. So, generally D algorithm is applied for a stacked fault. So, you can apply any other fault model even, but generally in this class we will be going to look about the stacked faults. Okay. So, one stacked fault at a time you are taking, because you have to remember that this D algorithm actually works for this it is the other way of test pattern generation, that is the non random based, that is we have random test pattern generation, and another is by sensitize, propagate and justify or logic based approach. So, this is for the logic based part, where actually we target one fault at a time, okay, and then we try to find out which is the pattern that detects it. Okay. So, that is why we will have only one fault. This is unlike the random test pattern where we can detect multiple faults in one go. So, we will be having a circuit with a fault, and then what is the output of the D algorithm? The D algorithm will tell which is the primary input values which will actually sensitize the fault, drive the fault effect to the output, that is the fault can test the, this input value can test the fault, and what is the actually also you have to tell what is the expected value at the primary output, that is if that expected value is not there in the primary output at that time, then it says that there is the fault. So, basically in other words, D algorithm formally tells you what is the pattern to be applied at the primary input to detect the fault, that is to sensitize, propagate and justify the fault, and also it will tell you that what are the expected value at the primary outputs at that time. Okay, so, if it matches the primary output expected, then the fault is not there, this fault is being considered, and if the pattern does not match the expected response, then you can say that this fault is there and it has been detected. Okay, so, now we will see what are the steps actually to go about this D algorithm. Okay, so, first thing is that all signal values of the circuit has to be assigned to X. So, this is the very first step that we take generally in the D algorithm. So, as I already in last few lectures we have already seen many ways of actually dealing with the sensitize, propagate and justify based approach, that is we sensitize the fault, then we propagate to the output and then we justify that, but that is not a very formal approach or way of dealing with it. So, this D algorithm will actually do the same thing, but in a more formal way using the procedures like implication, X drive and all those things, and some basic definitions like singular cover and all. So, using those things we will see it formally. So, in the first step you actually assign all the circuit values, all the signal values of the circuit to X. That means what? That is in the starting we do not know what are the signal values at the each net of the circuit. Then next stage is sensitize the fault. So, sensitize the fault you already know that if there is a stuck at 0 fault, then you have to apply the signal value 1, and if it is stuck at 1 fault, then you have to apply the signal 0. So, if it is stuck at 0 fault, then you have to apply a 1, okay, and that means in the normal case the normal case is 1, and because if the stuck at fault is there, then it is 0, implying that it is D, okay, in the fault location. Else if you stuck at 1, then you apply a 0. Then if the normal case is there, then the circuit is 0, and if the stuck at 1 fault is there, the answer is 1 at that net. So, the answer is D prime. So, therefore, you sensitize the fault. So, if it is stuck at 0 fault, then we write D in the fault location, and if it is stuck at 1 fault, we write D prime in the fault location, implying that this is the fault effect which needs to be propagated. Then in step 3, then once it is done, so the first step is actually make everything X, then you sensitize the fault, that is you write D or D prime in the fault location, and then you actually determine the gates in the J frontier and Day frontier due to changes in some changes. Okay. So, some changes why happened? Because you are actually putting a D or a D prime in the fault location. So, putting a D and a D prime in the fault location, now you have to propagate the value. Say for example, this is a gate, okay, and this is the fault location. So, you make it D, then there is a lot of combinational clouds. So, there may be 2 paths and there can be the third path. So, by this fault effect can be propagated. So, just whenever you apply this as a D, so automatically this gate and this gate will become a D frontier, because the fault can be propagated to this gate or this gate. So, similarly, so once this you know that if this fault has to be propagated, so maybe you get D at the output, then what are the other values of the inputs that need to be applied, so that the fault effect can be propagated to the D frontier, that means you have to detect these values. So, they will become your J frontier. So, what happens in other way, stating in the other way, so the moment you apply change X to D or D prime, that is you sensitize the fault, immediately the gates which are connected to the fault location will become the D frontier. That means you have to select any one of these gates from which the fault is to be propagated. So, say you find out a gate from which the gate is propagated, that is you select one gate from the D frontier. Now, what values has to be given to input of those gates in the D frontier or some other gates which are driving the gates in the D frontier, so that the fault gets propagated to the D frontier will now be actually falling into the J frontier. That means there we have to propagate backward and you have to find out which values have to be applied in the J frontier gate, so that the fault effect propagates to the J frontier. So, that is while you are doing step 2, automatically some J frontier and D frontier signal chains will appear. Then what you have to do? Then you have to propagate the fault effect to the D frontiers and justify to the J frontiers, and you have to keep on doing it till you reach the primary output, that is the fault effect is the primary output. But if it may happen that there is no gate in the D frontier and D and D prime had not reached the primary output, that means it can always happen, like say for example, I tell you. So, let us take a, we will all see detailed examples, but just to highlight the point, say for example, there is an AND gate and there is a stuck at 0 fault over here. So, you apply a 1, so you get a D over here, okay, you get a D over here because this is stuck at, okay, let me just try. So, it is a very detailed examples will be covering, but let us, it is really simple. So, this is stuck at 0 fault over here. So, you apply a 1 and you get a D prime, okay, and you get a D, sorry. Now, this is stuck at 0 fault, you apply a 1, so you get D, and say for some reason this gate is having input value of 0. So, anyway there is because this is the only path, because there is no other fan out from this. So, there is the only path where the fault effect has to be propagated is this, by this gate only. So, this is the only gate in the D frontier. But now, you find that to justify this you should get a 1 over here, otherwise the fault effect is on this. So, there is a clash. So, you can say that actually what do you mean by a gate in the D frontier, that this will actually not fall as a part of the D frontier, because I mean this gate is already, this fault is already 0, so the output is already 0, and there is no other path for this fault effect to be propagated. So, as this input is 0, so the output is always going to be 0. So, this net has no D frontier, you can say in that way. So, in this case, and also let us assume that this is not the primary output. So, I mean this is also not the primary output and this is also not the primary output. So, the fault effect D or D prime has not yet reached a primary output. So, you get a clash, and so you have to backtrack. Backtrack means you have to again try out some, I mean if there is no other, I mean if not, then this fault may be untestable, or if you have another option of driving the fault to another gate from the root, then I mean you can try for the other option. So, those things we will see in the detailed example, but what it essentially says that you take a fault, you have effect, I mean you apply D or D prime at the fault location, maintain D and D frontiers, and you have to keep on doing it till your fault effect or your D frontier reaches the primary output. But if you at some point of time if you find that there is no gate in the D frontier, that is somewhere your D or D propagation has been blocked and you have not reached primary output, then you have to backtrack. So, backtrack means it may lead to the case that the fault is not testable because there is no other option left for driving the fault to the output, or it may also happen in other way, that is there is some other option, there are other gates which you could have used for the fault effect propagation by other gates in the D frontier at some previous step. So, you can try for that. Okay. So, now right. So, that is what it is being said. In step 4, if D or D prime are not in the primary, propagate D prime through one of the gates in the D frontier. Okay, so I mean that is this step it is saying. So, if there is no D frontier, then you backtrack. Okay, if this is not the case, then you update the D and J frontier, and then if there is some gates at least in the D frontier, then what you do? You if you have not yet reached the primary output, propagate D or D prime through one of the gates in the D frontier. That is, you get D or D prime by sensitizing the fault. Then if this is the case that there is no gate in the D frontier, then your algorithm you have to backtrack and do something else. Okay. But if there is a number of gates which are in the D frontier, then you have to select any one of them the gates, and you have to propagate the value of D or D prime, and you have to do this until you reach what you call the primary output. Okay. So, now once you have jumped one gate, that is when you have propagated the value of D from one gate in the J frontier, you have to use forward and backward implication to determine as many signal values as possible. That is, you have to go for implication, or you can also, that is implication, or you have to justify the gates in your J frontier, and then what you have to do, you have to at any point if you get a backtrack, I mean any point if you give an inconsistency, that is you require a 0 or a 1, but actually the signal is other way around, that it is 1 and a 0 in the respective respective cases, that is I mean you want 1, but already signal is 0 and other way around, then you have to say that this is not possible to justify the gates in the J frontier, and then you have to backtrack and use some other option which is left. So, whenever you have moved the that is what actually we said, say for example, this is one gate, so this is say D, and then you propagate the value of D here, and through this you say that there is an OR gate over there. So, you know that for the fault effect to be propagated, so not D prime, it is D. So, this is D and then it get effect output to this gate. So, you know that this value has to be a 1. So, immediately you have to put x1 or 1x to the OR gate. Okay, so I mean in the last class we were discussing that why you want to put x1 and not 1 1 or the other way around, that is always we try x1 or 1x. Why not 1 1? Because 1 and a 1 in the OR gate or x1 or a 1x in the AND gate, OR gate is always a 1 which will satisfy your case, but you always use x1 and 1 or 1x, but not 1 1. So, we will see what is the problem if you are hard coding the signal values like 1 1, that is we are not, if you are putting 1 1, then we are not using the concept of singular cover. But what is the importance of singular cover, that is we were discussing, but we have not yet given example to illustrate it, so which we will see in the question answer session. But for the time being, just take it granted that 1x or x1 has to be used so that you get the value of 1. So, how do you get it actually? So, I mean if this is D, so initially all the signal values will be actually x, this is also x, this is x. So, you know that this is x fine, so the value of this has to be fault effect has to be propagated to this. So, this is the gate which is in the D frontier. So, now we will get the value of D over here. So, now once you get D, so you can think that this actually is becoming a J frontier kind of a thing, and by backward implication you can say that this value has to be a 1 for the fault propagation. So, immediately if this is 1, so this gate will follow in the J frontier, and by backward implication either x1 and 1x is to be there. So, whenever and then you know that I put x1 or 1x, then you get the value of 1 here, and D automatically propagates over by this gate. So, that is what is being said by step 5, that use forward and backward implication immediately to determine as many signal values as possible. So, when you are propagating the fault value fault effect D or D prime from one level, at the same time immediately you do backward implications and by justifying the values of the J frontier gates or otherwise, and then try to solve as many x's as possible. But it may also happen that there can be inconsistency, that is you require a 1, but you are getting a 0 or you have to apply a 0 kind of a thing. So, in that case of clashes you have to again track back, that is if there is any other option of using another gate in the D frontier or another option of trying out with what you call this because you see we have seen x1 and 1x, they are the two signal values which are applicable for justifying the J frontier. So, if you find that x1 is fine, but 1x is not fine, then I mean say you get 1x, then you find that 1x is not being satisfied, then you have to try x1 kind of a thing. So, we will determine all these things in detail. So, by backtrack we means that at any step if there is some option available, option means one of the, if there are n number of gates in the D frontier, you take any one of them. So, in this case, I mean if you have taken one and you have failed, then you can try with the other gate. Similarly, like when you are justifying a gate in the J frontier, so one case for this in last example we have discussing was x1 and 1x. So, you try 1x, then you find that 1x is not solving your purpose, so you can use x1. So, there are some of the options. So, by backtrack always means that you have to try out for options. And in this text 6, if D or D prime is any primary output, then the primary input value received by backward implication, then stop the values of the primary input compare the test pattern, else you have to again repeat keep on doing from step 3. So, this these two steps, that is you propagate the value of D or D prime one step ahead, immediately justify immediately what you call by implication of the inputs of the gates in the J frontier, you solve as many x's as possible and you keep on doing it till your D or D prime has reached the primary output. So, if your D or D prime has reached any of the primary output, that is your fault effect have reached the primary outputs, then your job is done. So, immediately you find out solve the x's from the inputs, and if some x's are still there is not an issue in the primary inputs, because that states that it can be either 0 or 1, you need not bother about it. But just when your D or D prime has reached the primary output, then you should be very happy that your fault effect has reached the primary output, and whatever is the signal values at the primary inputs, that becomes your test pattern, and whatever is the fault effect at the output, that says that the expected primary output for the test pattern is so and so. So, for example, if your primary output you get D and some input pattern at the time, input values at the time is 1 1 1 1. So, it will imply that the input pattern is 1 1 1 1 for that fault, and what it says that if your output is D, so it says that if it is 1 1 1 1, then in the normal case the answer will be 1, and in the fault case the answer will be 0. So, that is what is being implied by the automatic test pattern generation by D algorithm. So, once your job is done, once your fault effect, that is D or D prime, reach to a primary output. So, once it is done, you can stop track, I mean, and also you have to observe that, you have to take care that there should not be any x in any of the intermediate nets. So, if there is any x in the intermediate nets, then you have to justify them using the backward implication of the J frontier gates, but if there is no such x in the intermediate gates, in the primary output if there is only some x's, then you need not bother, because x's means you in the primary input means you can be, it can be either 0 or 1 in the primary output, that will not hamper in any way the fault detection of that primary input. But still, if your D or D prime is not is the primary input, primary output, sorry, then you have to go back to step number 3 and keep on taking the value of D prime one step ahead from your, what do you call, one step ahead from one gate to the another gate. So, all these things we will now see in a short while in details with an example. But as I told you that there is some backtrack. So, what was by backtrack meaning? So, this slide actually elaborates what is a backtrack. So, what was mean by a backtrack? So, backtrack means what? Say for example, there is a clash, that is you wanted the signal value to be 1 by backward implication of the J frontier gates, but for some reason that is 1 by some other cases and so forth. So, in this case you have to backtrack. So, and you have to try other alternatives. So, what is the determine the last choice of the alternative taken in selection of the gates in the J frontier or signal values for backward and forward implication of the J frontier where a new alternative is available. So, what does it say? Say for example, there were a lot of choices in the gates in the D frontier. So, you took any one of them. So, you can try with any other of them. Similarly, there can be number of signal values, like for example, if it is an OR gate, so you want a 1, so it can be x1 or 1x. Similarly, for an AND gate, if you answer to be 0 if you want, so it can be x0 or 0x. So, there are two choices available. So, these are some, it is saying that signal values in forward and backward implication of the gates in the J frontier. So, there are some alternatives. If you tried with this one, now you can try with this one. If you have tried with this one, now you can try with this one. So, try out, undo. So, say for example, we reached an inconsistency, then you undo all these steps. So, what do you mean by undo all these steps? Undo all these steps means till wherever you have given some, you have converted some signal values of x to some values like D prime 1 0. So, you make all the signal values x and reach to a place where there is an alternative available. Like for example, we started with a case, say for example, this is an AND gate. So, it was stuck at 0, we applied a 1, we got D, and there is say 3 gates, 3 nets. So, this is one D frontier, this one D frontier, and this is one gate in the D frontier. Say for example, we have selected this, then we found an inconsistency in some place, then we backtrack up to this point. So, what do you mean by backtrack up to this point? That means all the signal values which we say that we propagated the value of D here from here maybe D prime and so forth, some propagation we have done, and some, that is we converted some signal with values x to 0 1 to x, from x to 0 1 D or D prime. So, you have to undo all them. So, everywhere you have to put value of x, x and x, okay, till this case where your option was there. Then you said that by this path your things have failed. So, you start working with this path. So, similarly, so doing backtrack undoing means you have to convert all the signal values from 0 to 1 or D prime to x till you reach the point where there was an option available. Similarly, for example, if it is an AND gate, you require a 0 over here, you use x0, then you find out a failure. You keep on backtracking and change all the signal values from 0 1 D prime to x, then you find out that there is a problem over here. So, you now change the option to x0 and again try out. So, this is actually called excuse me, actually this is called a new alternative, and what is actually called, you nullify the effect and this one. Okay, so, now it happens that if at some point of time you find that there is no choice available, then you say that the fault is untestable and the fault cannot be tested because of redundancy or not. So, that also one example we will see when we will be going in the question answer session. So, what is saying undo all steps, that is what is being discussed by step number 2, and undo all step means actually propagation of D prime and backward the current signal values, I mean where the last is attempted, that is what is I was discussing. So, actually undo all these steps means, so what is the backtrack says that? Backtrack says that you undo all these steps till you reach an alternative and then start with another option. So, that means what? In a very broader sense, what this step says that you found out an inconsistency, come back to the point where you get a, where there was a more than one choice, and from the point where you backtrack to the point where there is an option, make all the signal values, that is undo all these steps. Undo all these steps means you change the values of signals to x from 0 1 or D prime, that is you are doing undoing, and you try another alternative. But if there is no other alternative available, then what you have to do is that then you have to declare that nothing was possible, that is there is no other choice available, and what you say, that is the fault is untestable and so on. So, I mean what is the idea behind this one? The idea behind this one is that try out all the choices. That is why this D algorithm is called a very expensive algorithm, because you might have seen in the last few module lecture that sensitize, propagate and justify is successful in all these steps. But in today's example we will see that it is not the case. Many times you will have inconsistency and then you have to try out many other alternatives. And as a circuit has, generally a circuit has lot of fan outs. So if there is a lot of fan outs, so from the fault location there will be a lot of options in the D frontier, and so if you fail in the first option then you have to try for another option and keep on doing it till you successfully propagate the fault effect to the output, and that is what is the killing point of D algorithm. So had it been the case that your D algorithm always successfully you can select out the best option. See, the general case is that faults are untestable, means generally there is redundancy in the circuit. So there are very few faults will be there which will be untestable. But then why do you call that D algorithm is a complex algorithm? This is because many a times we cannot hit the correct option at the first time. For example, there can be one among the n D frontiers and n j frontiers, there can be only a very few choices through which the fault effect can be propagated to the output. So but it happens that you try out with option 1, then you fail, then you come out to option 2, then you again fail, and you can understand that this is actually a very, it blows up in complexity, because say in the first level there are 2 gates in D frontier, second level there are 3 gates in D frontier, then there are 2 gates again in the D frontier and so forth. So you have to try out, this is option 2, then from there can be option 3, then there can be option 3 from this, then can be again 2 options. So it grows like a NRE tree. So that is number, if you have to try out all the options exhaustively, then you have to traverse this NRE tree. So at each level, if there are n different options available in the D frontier or J frontier kind of thing, so it actually blows up exponentially. So that is what is the difficulty of D algorithm. But if you could have made out an intelligent D algorithm, which is actually we will see in very brief, that is PODEM and FAN and henceforth, that is they intelligently do the backtracking. And if there is some intelligent search in the tree, then D algorithm will not be that complex. But in the general sense, what happens, you keep on trying out the options one after another, and that is actually the killing point of this D algorithm, or it becomes very complex because you do not have a very guided direction of search. But now in the advanced algorithms, the guided directions of searches are slowly coming into picture. So, but again there are advanced algorithms which are not much discussing in this course, but generally the idea is that because of the advances in D algorithm and henceforth are to find out good search spaces. I mean, among the big search spaces of the NRE kind of a thing we have discussed, they find out good tracks. Like for example, you have failed in one path, then you use the information that why you have failed in that path and use that information to select a better alternative for the J frontier and the D frontier in the next search. So that is how it goes on. So but had it been the case that D algorithm is always very successful, that sensitize, propagate and justify happens in just in one go, then D algorithm would have been a very similar in complexity to kind of random test pattern generation. That is, I mean, you cannot compare it that way, but it would have been another very good alternative compared to random test pattern, even for the easy to test fault. But this is not the case. Generally for many of the options, you will find that you have taken a wrong decision and then you have taken backtrack and keep on doing it. That is why only for the difficult to test faults we use D algorithm and its variants, and for the easy to test fault we go for random test pattern generation. So I mean the D algorithm or the life is not very green here, because there is lot of options and many of the options you may prone to take a wrong option and then again you have to backtrack. That is, and the number of faults which cannot be tested is not very high, but in that case you have to try many options and you will fail. But that is not the killing point. The killing point is that for a successful case, I mean about 99.9% faults will be testable in a circuit. For all the successful cases, it is still there are a lot of options available, and it is the duty of the algorithm. D algorithm is a very plain algorithm because it is the first algorithm of its kind in ATPG. So it does not say about how which way or in which way you have to select the options, but advanced algorithms do tell you a guided direction of searching the alternatives. But if you talk about D algorithm, it does not give any option, so you have to randomly keep on exploring the state space, which is actually making it very complex. Okay, so that is what is the brief discussion, that why we most prone to go for random test pattern generation as much as possible and apply D algorithm only for difficult to test faults. Okay. So now, because many times you have to go for lot of backtrack. So now here we will see an exhaustive algorithm, exhaustive example, so which will tell you how exactly D algorithm works, and you will also see many cases of backtracks over here, so that it can give you a very good highlight of that D algorithm. There is a lot of options possible. Always it may not be as green as it looks, that always will be successful. Sometimes you will have to fail, you have to take many other options and do it. But we will see in the very formal notion as we have discussed the kind of D algorithm in the last few slides. So let this be the circuit. So you can observe that all the nets are having x. So it has been all initialized to x's. So there is all the places has been initialized to x. Now this is a stack at 0 fault at this one. So, we want to find out a test pattern by sensitize, propagate and justify approach of D algorithm for this stack at fault. So, this is the first step and you know that. Okay. So, now next. So, what is the case? So, now stack at 0, so you have to apply a 1 over here. So, that is a very straightforward we know. So, normal case 1, fault case 0, so you will get the value of D over here. So, now once you apply D, so by definition of D frontier, so what you know that there should be a gate from where you actually you can pass out this fault. Okay, so you can observe that this is the fan out. So, initially you can say that these two are actually F and this. So, this will these two options can be used for propagating the fault effect. So, this is a gate whose one input is actually, these are the two gates which one input will be D, this X can be eliminated to D by this fan out. So, because you have to already know that this, let us go back a few slides. So, you can see this D algorithm. So, you can see that this is for the fan outs, this stuff is like this. Just a minute. So, you can see just the definition of just we are very quickly see the case of this D frontier, the same kind of this thing. So, you can see that the inputs are D. And so, what is the D frontier comprises gates whose output is X and at least one of it input is D or D prime. So, just a recall of the definition that D frontier comprises of a gate whose input is D or D prime and the output is X. So, you can see this one by this definition of D frontier, that the output is X and one of its input is Z. So, obviously, these two gates will be part of this D frontier. So, we write that 2 and 3 are in D frontier kind of a thing. Now, you see J frontier. So, you know that this is D. So, this value has to be a 1 over here. So, what is the definition of a J frontier? J frontier says that a gate whose output is 0 1, that is known. So, this output is D. So, that means you have to know that you have to apply a 1, but inputs are X. So, this gate, so it has to be 1. So, by backward implication you have to justify that how you can get a 1. So, this gate number 1 will be a part of D frontier, sorry J frontier. So, J frontier, as we already discussed, that it mainly handles backtrack and D frontiers go for the forward direction and J frontier tells you about backward direction movement. Okay. So, now what happens? So, this gate output is 1, we know, to sensitize the fault, both the inputs are X. So, this 1 will actually part of J frontier and fault effect, this D, input of these both the gates are D and output is X. So, this gate will actually, these two gates will fall as a part of our D frontier. Now, our choice is, so here is the choice, you have to remember that this is the point of choice, the point of choice over here. So, you can take either this gate or this gate for this fault propagation. Okay. So, these are point of a choice, you have to always remember the choices of a point. So, now what happens? So, first as I told you that at every step when you are actually what you have done. So, if you propagated the, say for example, you have sensitized this fault. So, just you are sensitizing the fault or you are propagating the fault effect to one of the D frontiers. So, automatically we will create some J frontier. So, once you have done this, so some D frontiers have been created and some J frontiers have been created. Now, you have to slowly resolve this J frontier and the D frontier. So, J frontier is you require a 1. So, this is very XX. So, obviously, you require 1 and a 1. Okay, because that is by singular cover problem. So, if you have a 1 over here, the inputs of the N gate should be 1 1. Okay, so you apply 1 1. So, that will solve your J frontier that will resolve this J frontier business. Now, your J frontier is empty because you have solved the problem of J frontier by backward implication. Now, this 2 or 3 they should be D and a D. So, you should remember that now these two gates are in D frontier. So, you have to take any one choice of this two stuff. Okay. So, now you just think which choice is there. So, it has been written that 2 and 3 are the possible D frontier this thing. So, you have to select any one. So, for example, this guy, because I told you D algorithm is a flat algorithm. So, it will not use any kind of estimation to tell either 2 is better or 3 is better. So, but the advanced algorithms like which is PODEM, FAN and other algorithms which are advanced version of this, they will tell you or they can give you a guideline that you take 2 or 3 which one you use for the propagation. But as this is not the case over here, so we will not directly go for that. So, we will go for the traditional D algorithm as we are dealing with that. So, we will take 2 for arbitrarily we are taking 2 for our fault propagation. Okay. So, 3 we are not considering. So, so this possibility of D was also there, but we are not considering the fault propagation through this. So, for the time being you can keep it as X, that is not an issue. So, we are going to affect the fault propagation over here. Okay. So, there was 2 choices because this D was here and this was there. So, now we are going to propagate the fault effect through this. So, we will keep back it to x. So, we will see the motivation of that, why we are trying to keep more number of lines as x if there is a chance. So, that we will see with an example in the question answer session. So, we could have also written a d over here, but for the time being we will not write this. I mean, we can maintain this, but for the time being, as we are not propagating the fault effect through this, we are only propagating the fault effect through this. So, we will maintain a d over here. Okay. So, the modified d frontier is only x and 3 we have deleted, because to delete, because if d would have been here by definition, 3 would have also been in the d frontier, because one of the inputs is d and output is not known. So, is the possibility of fault. I mean, d frontier says that one of the input is d or d prime and the output is x. That means, there is a chance of propagating the fault effect to this gate. So, if I write a d over here, so 3 should also be the part of the d frontier, but the designer or the test engineer has decided that he would propagate the fault only from this one. For the time being, we do not maintain it as a d, but in fact it will be d only, because the fan out, the fault at the fan out step. Okay. So, this is what has been done. So, it has been selected, you write a d over here and this is the case. So, now, so this was your d frontier gate. So, you will have to propagate the value of d. So, you know that is a d over here. So, and one of the input in this case was an x. So, it actually is propagate the value of d over here. So, this gate is x. So, you can think that this is a type of a j frontier kind of a thing. So, in this case by backward propagation you have to get the value of a 1 over here. So, I mean, at this point I want to mention that strictly by the definition of j frontier, if you look at the very strict definition of j frontier, so it says that, so there is some we need some discussion over this. So, j frontier will actually tell you that the output of the gate is 0 or a 1. So, it says that, what is j frontier saying, that the output of the gate is known to be 0 and 1 and its inputs are not yet known. So, it says that, for example, some gate is there whose output is actually for in this case, say for example, you know that this input is d. And so, in other words, this is a gate, say for example, this output you know is to be 1 or 0 and both the inputs are x. Actually, this is what is saying, a gate whose output value is known and its inputs are not yet computed, that is, you do not know the value of input. So, in the last class also we have seen that for some example kind of a thing, like some fault effect, maybe this, for example, in this case say the fault effect may be some d over here, and we do not know. So, I mean this example already we have discussed in the last class, that very simply that this is the case. So, you know that this d will be propagated from here to here, as you are discussing like this, the input is not known. So, you can consider this as the j frontier. Okay. So, there is a sometimes we do not call these things like that is some of the so in this example. So, what we have seen that the one of the input of the gate was a d, sorry, one of the input of the gate was an x and the other input is d. Okay, and the output you have also considered to be a d. But now, sometimes we may call that it can be very easily justified by a backward propagation, that by backward propagation means one input is d and the output is the AND gate. So, that input has to be considered to a 1, but sometimes it may also happen the other way around, that is both the inputs are x. So, very strictly speaking, sometimes people say that both the inputs are x, or even if it is a 3 input AND gate, the 3 inputs are x, it may be the case that is all the inputs are x and the output is known. So, very strictly they will say that that is the only gate in the j frontier, and the other gate where one input is known and the other 2 inputs are x, then you can say that you can solve this using a what you call this backward implication, but strictly they may not call it as a d frontier. Okay. So, the next step which we are saying that, so you have considered so, we are saying that this gate, the person has selected the gate number 2 as d propagation for d. So, you have propagated this point. Now, you can see that the output of this gate d is known and one input of this was x. So, you can think that this is a kind of gate in the j frontier, and by backward implication this was already known to be d. So, you can say that a is equal to 1. So, that is by the j frontier back propagation you can have done it. So, it is saying that now you can see that propagate d to the j frontier and backward implication, that is the 2 in the j frontier, and immediately you have solved it to be 1. So, okay. So, very strictly you may not call it as a j frontier kind of a thing, because just one input you can very easily do it by backward implication, but in the definition terms you can, I mean in the formal terms which we are discussing the algorithm, you can say that as this input is unknown, so it is a j frontier and you can easily make it 1 and solve the problem, that is backward, and justify this input. So, justify this input so that this fault d is propagated. The idea was that 2 is selected as a d frontier, fault effect is propagated the output. Now, input d is known, this one input was x. So, by backward propagation for this gate 2, you make it a 1 and everything is justified. So, we have already discussed that backward implication for J frontier and forward implication for the D frontier kind of a thing. So, now you can see for this gate, now what happens? So, your D is here, that is only one path where you can propagate your D. So, at this all the time you have to observe that there is one X path. From this path to the output, you see there is a path which is having all values of X over here. Already we have discussed in the last lecture that for the fault effect to be propagated from the D frontier or from a set of gates in the F frontier, there should be at least one path where all the nets are having an X, that is this path will be used for fault propagation. So, if there is some gate where the value of X is not there, so it is 0 or a 1 or some way it happens, like for example, for some reason say we can say that this gate has become a 0. So, this effect will be a 1. So, there is no X path from this point to this point. So, the fault effect propagation will be stopped at this gate and the fault cannot be detected. So, what we have discussed in the last lecture that this fault effect will always has to be this fault effect is D from this gate in the D frontier, there should be at least a path which is an X path. So, in this case there is an X path available, so this fault can be testable, may be testable at this point, we can say that. Okay. So, now there is one gate 4 in which the one of the input is D and the output is X. So, we may think that this fault effect may be propagated to this. So, the modified D frontier is gate number 4. So, when we call a gate in D whenever when we call a gate in a D frontier, we call a gate in D frontier if and only if one of its inputs is D or D prime and the output is X. That means, there is a scope of propagating the fault value to the output. So, it happens in the case of gate number 4. So, easily we may say that now gate number 4 is in the D frontier and this 2 is deleted from the D frontier, because once the fault propagation has been done, we have seen this in the last lecture that you have to delete it. So, 2 is deleted and 4 becomes in the D frontier. Now, so this is your D. So, now what happens? So, you know that if it is to be a D, this is a D. So, what is the values for the D to be propagated? So, by backward implication, you can think that the value will have to be a kind of a 0, because it is only when the value is 0, then only the fault effect can be propagated. So, you can think that whenever D is over here, so gate D is in the D frontier, but just after you propagate the value to here, then it no longer remains a gate in the D frontier, you have to delete it. Okay. And then the output is known, but the input one of the input also you know obviously, the other input is not known. So, you can get it by backward implication, and then that is very easy to say that you can very easily you can handle the case and you can say that you have to apply a 0. So, you can think that you are just justifying backward for gate number 4 by using the J frontier properties. Now, so this has been done. Now, you can see that now question of gate number 3 and gate number 5 has been propagated. So, has arisen. So, what we have seen that whenever there is a propagation of this D or D prime, some new D frontiers and J frontiers arise. So, in this case what happened, you propagated the value from here to here. So, immediately 4 is deleted from the D frontier list, but it creates a problem for this. I mean, you have to find out what is the signal value here, and then also it creates D frontier for because it creates a J frontier, because you have to find out what is the value of this net number k by backward, and also it will create another J frontier for 3, because you have to also find out the value of these 2 nets, okay, as well as it has also created a new D frontier gate number 5, because there is a chance of propagating the value of D from here to here, because the output is X. So, this propagation actually is creating 3 things. One, gate number 4 you can call to be a part of J frontier kind of a stuff, because this signal value output is known, but one of the inputs is not known. So, that has to be done by backward implication. Now, once this is done, so once you solve this problem, that is you put a value of 0, next moment another gate arises, that is the output of gate number 3 is known to be 0, but these inputs are X and X for which you have to know the value. And how do you know the value of this one, correct? And then another gate, this is say we can say that this is number 2, and also one more thing is created, that is number 3. So, that is what? So, you get the value of D over here. So, there is only one path, there is a gate, the gate number 5 where the output is X and the input is D. So, this gate can be a tentative candidate for propagation of the effect. So, it will become another gate in the D frontier, sorry. So, modified D frontier is 5, modified J frontier is 3. So, sometimes by Steer definition, that was saying that sometimes we do not very exactly call gate number 4 as a J frontier. Why? Because one of the inputs is D, the other only one more input is unknown. That is we just say that it will be a 0 by backward propagation, but one of the inputs is known. So, only one more input you have to justify. So, we may not call this as a D frontier in a very strict term, but even if you do it, I do not see any harm in that, because J frontiers are responsible for backward implication and D frontier are responsible for forward propagation. But now for the gate number 3 you can see that both the inputs are x and the output is known to be y. So, by a very strict definition of J frontier, the D will be highly in the very strictly it will fall in the J frontier definition, because output is known and both of the inputs are unknown. But to my understanding, you can also call 4 to be also a part of J frontier once this D has been propagated to be there and it has been deleted from the D frontier list. You can immediately call it, because you have to justify this. But now, so it is somewhat you can call, sometimes some definitions are very strict, sometimes you follow them strictly, and sometimes we can also with a slight abuse of notation you can call them both to give a very coherent feeling for both the definitions. So, for me now, for once you have decided this signal to be 0 by backward propagation. So, this gate number 3 will be in part of J frontier and gate number 5 will be in part of D frontier, because this will represent the propagation of the fault effect of net H, and this for gate number 3 you have to get a 0 at the output. For that you have to find out this value of signal at x, signal x at J and signal x at D. So, now let us see next what happens. So, how do you get a 0 at the output of the NAND gate? So, it can be only by 1 and a 1. So, by this D frontier propagation you have to say that I will get a 1 and a 1 over here. Okay, so, that is what is the case. So, modified D frontier is now 0. So, you have to apply a 1 over here and 1 over here, that is being told over this case. Now, what you see immediately, now what happens? So, now you get a 1 over here. So, immediately if you get a 1 over here, the output is known. Okay. And what do you call? So, if this out, as earlier discussed, if the output is known, so we require also a 1 over here, that is because of the backtrack or the J frontier for the fan out stem, but we already know that this is a D. So, there is actually a clash over here. So, backward implication we require 1 at the output of this gate, what is at D. So, there is inconsistency and you have to backtrack. Okay. So, also we have discussed that sometimes we would have also said that in the first slide of this lecture, first slide of the example, we said that this was an x and this one was also an x. Very first slide, just if you look at this example, we were discussing that why we are putting an x kind of a thing. Yeah, this example. So, so both were x. So, we found out an inconsistency at this point, because we required a 0 over here kind of a thing. So, for that you require a 1 over here and a 1 over here. So, that was a point of inconsistency. So, but in the first step we said that as we are going to propagate the value of D over here, so let us make this D over here and keep it x. Okay, we are not converting it into a D over this one. Okay, but we could have also said that this is a D. We could have also said that this is a D because of this fan out propagation, that because the fan out will be D, so obviously these two nets will be a D. So, even if you are propagating the value of what do you call this fault effect to this D frontier from gate number 2, but still we could have said that this input number also net number J is D, but we have not done it. We have said that we are keeping it x and we are giving a scope of applying a 1 and a 1 over here. So, that we are trying to establish a 0 over here. So, for that we require a 1 and a 1 over here. So, we are trying to make this effort over here and then we are finally ending with a clash over here. So, now you can ask me the question that in the very beginning if I would have put a D over here, then what would have been the case? Then I would have said that for this gate number 3 I need a 0 over here. So, I require a 1 over here and I also require a 1 over here. Then there could have been detected that there is a clash and I could have stopped here. I could not have, I may not have moved up to this step. So, you could have saved one step in the computation, that is this D over here, but I require a 1 over here to make it 0. So, there is a clash and I have stopped. But in this example, but by exactly following this algorithm we are discussing now. So, what we have done here is that we allowed it to keep it x, we allowed x over here in this point, and then what happened is that we had to resolve this clash at this target point. Okay, so, there you can say that there is a one more step which is having a problem, that is so there is two ways of saying it in the approach we have taken. So, we are keeping as many x's as possible, then we are saying that we have lost one step or we require one more step in the computation. But if you have taken the other way around, that if you have applied a D over here in the time for the initial, if you have applied a D in place of J, then our backtrack or our inconsistency would have been caught in net number J itself, but now it has been caught at the output of input number 1. So, we are subbing on, but actually we will see through an example that we have to keep, but this example is not very suitable to show that, but in the end we will see an example where we will see that if we keep as many x's as possible, there is a more probability that your inconsistencies are less. But if you hardcore more signals, like if we could have hardcoded a D over here, okay, or we could have hardcoded a 1 at some places, but if you do like this, then what can be the problem is that many times we will land into more number of inconsistencies. Then we could then the case that when we are not hard coding the signals, that is in this case our conflict occurred at the output of gate number 1, but if you hard code the signal, then our conflict would have occurred at the gate number J. That is, in this case this is a good thing that our computation we are able to catch the effect of the fault much beforehand, but so in this case this is a boon, but generally by putting more number of x's, we are trying to defer the conflict as much as possible. So, somehow if we could have deferred the conflict to the primary input and beyond, then we could have been very successful. That is, the philosophy is keeping more number of x's will delay your conflicts. So, if you can somehow delay your conflicts to a reasonable amount of time and pass it to the primary inputs, then your problem is solved. So, that will very clearly we will see with an example in the end, but in this example you could have argued and which I should have been accepted that it is the case that if you put a D in case of J, then your conflict would have been caught at J, but as we are not doing it by strictly following the D algorithm, our conflicts get at the output of gate number 1, so one more step delay. But we will show with an example that this delay can be tolerable, but generally by putting more number of x's, our circuit is more flexible and more prone to delay delay the conflicts, and sometimes we can even avoid the conflicts by putting more number of x's. So, that we will see in an example in this thing. So, now we will go to this next step of this one. So, that is we have seen that there is an inconsistency, but actually now instead of detecting the inconsistency over here, we have detected the inconsistency over this thing, but at this has come out of cost of putting a x over here, but in the example we will see that x also has a advantage like deferring of this one. So, now let us not look too much at this advantage or disadvantage of putting more number of x's, because there is a secondary element in D algorithm, but the primary algorithm is primary job of this algorithm is to find out the solution. So, we had a inconsistency at this point. That is, at this point there was an inconsistency at this net. So, if you have got an x over here in this net, if you could have put a D over here, so your inconsistency would have been caught here, but now the inconsistency is caught here. So, but anyway there is some inconsistency at this point, you can think of this way. Just one step ahead or one step this one, the inconsistency is caught. So, now at this point, so what we had a choice of this and we have a choice of the D frontier. So, they discussed that wherever there is a choice, so you have to take the alternative choice. So, in this case we have taken we have to take as there was if there would have been no other choice, then we should have declared that this fault is untestable. But now we have a choice at this point between gate number 2 and 3. So, what we will have to do is that we have to take another choice, that is gate number 3, because there was a choice of 2 and 3 and the D frontier. So, now we are among these 2 and 3 D frontier, we are taking the D frontier to be 3. So, as I told you that this is D, so this is D and this should also have been D, but to keep the circuit more flexible or in kind of some way of delaying these clashes as much as possible. So, we are keeping it x because we are considering this to be the gate in the D frontier. And you also observe that when you are doing the backtrack, all these points are again made x. That is what is the type, that is what we already discussed, that whenever there is a kind of what you have to do, that whenever there is a backtrack you are taking another option, then you have to make all the gates to be x. Correct. So, all these x's has been done. So, now this was in the D frontier frontier gate number 3. So, now you put a D prime over here. So, once you put a D prime, it will be obviously this is fault effective propagated. So, because this becomes a D prime inverting gate. So, now you can see that this gate number 4 will be in the D frontier because this output is x and the input is fault value is D prime. So, there is a scope of propagating the value through this. So, it becomes a gate in the D frontier, gate number 4, and in by J frontier algorithm or J frontier procedure, you can think that this input output is D prime, input is D. So, this value has to be a 1 to justify this one. So, by J frontier in gate number 3, you have to put a D 1 over there. Okay, so, this is the modified step, next step. Now, what happens? So, you get a d prime over here, the output is x. So, obviously, this gate will become a part of your D frontier, because there is a there is a what you can call there is a probability that is this fault effect can be propagated through this one. So, this one will become a part of your new D frontier, correct. So, one more thing that is the case, that is we are propagating this value to the output here. So, this value is there. So, by these two things are there. So, one number thing is that gate number 5 is becoming your gate in the D frontier, as well as because of this propagation. So, we know that this by the concept of J frontier for gate number 4, the value has to be a 0. Why the value has to be a 0 over here? Because the output of the AND gate or gate, if you have to propagate the value, this value has to be a 0. That is a very well known fact. Now, also you can see gate number 2. So, what happens to gate number 2? The output is known to be 0 and both the inputs are x and x. So, again this gate number 2 will become a part of a J frontier, because you will have to go for the backtrack business, correct, and the modified J frontier, this is number 2 which you have done. So, what we have done actually 3 things again. So, the fault effect you have propagated over here. So, first thing is that gate number 5 will become a part of a D frontier, because next step there is a probability of propagating D prime through this. Next this value, what is the input of another input value of gate number 4, so that this D front the fault effect D prime can be propagated through gate number 4, that is a 0 has to be applied over it. So, that can also be solved by backtrack, that is going for a backward implication of the J frontier of gate number 4. So, you can say that this is point number 2 that is being done, as well as whenever this value of 2 the 0 has been done here by backward implication. So, immediately you know the output is 0 0 and the inputs are x. So, gate number 2 will become a part of a J frontier. So, these 3 things 1, 2 and this is the third thing. So, these 3 things happen. Okay. So, these next step in the D algorithm for this propagation, right. Now, again as I already discussed that output of this AND gate is what. So, now you have a D over S. So, all these steps are there. So, you know that now you are concentrating about this one. So, you know that the output of the AND gate is 0, and so what can be all the possible cases of the case. So, we know that by singular cover it can be x0 or 0x. You already know that, correct. So, now let us try the case of we require a 0 over here. So, we require a 0 over here. So, in this case you could have put a this is a mistake on my part, a typo. So, actually you require a 0 over here. So, you could have said that is x0 or that is this option has been taken, but there could be another option that is 0x. That is, you could have also taken a 0 over here and you could have kept an x over here. So, that was another option, but for some reason see that this person has not taken this option, he has taken this previous option, that is x and a 0 over here, correct. Now, so this is the case. Now, you can take this picture, and now so by modified J frontier, so 2 you have stated to be 0 and x by singular cover. So, this becomes 0, and now you can see that also you could have said that I would have moved this one. So, you will get D over this, and this could have been a 1. So, this is one more step you could have done it, but you see there is another inconsistency that has started place. We will be just immediately detecting this, because you require a 1 over here, and by this backward implication for the J frontier in gate number 2, you are saying that I require a 0 over here. So, there is again an inconsistency and it is a stop over there. So, now what you can do? So, let us see another way of doing it. So, how do you do that? So, one more option was there, that is, you will see that there is one more option that was in the AND gate. So, there is 2 options of getting a 0 over here. So, one is x0 and that is 0 and x. So, last slide we tried with this option and we found out that there was an inconsistency. So, let us try with another option, because here there was again another option available. So, what we are doing here now, we put a 0 over here and we put a x over here, that is this option we are trying. So, now you see, so again the J frontier will be 2 will be there in the J frontier, and once you do this it will be again deleted. So, now let us see what happens. So, you require a 0 over here, you require a 1 over here and all this. So, this already we state that if you propagate this here, so you should get a 1 over here, that is fine. So, now you get a x over here. So, now what is this case? So, that is fine. So, what does this x here means? So, x here it means that it can be anything, that is the output 0 here is not at all dependent on whatever activity over the slide. So, that is why we are keeping it x and not a d. So, you could have also put a d here, we could also put a d over here and we could have done it, but now we have not done this because we are considering 3 as the d frontier. So, now the other option we have instead of trying an option of x 0 which created an inconsistency again, so we tried with the other option, but whenever there is a conflict we just go back to the last option where we had made a mistake. So, last option was taking wrong thing was taken was the concept of taking an x 0 that was creating the problem. So, there we stopped. Okay. So, now we reverted it back and then we are saying that we will apply 0x. So, now 0x says that the whole solution has been done because we require output 0 over here to solve the problem, and this x here stands for saying that whatever be this is d prime 0 1 whatever may be the case, the output here is not dependent on this one. So, 0 over here will solve the problem, and also this prime this d prime has been propagated. Sorry, it is not a d prime, it is a d. So, this d prime has been propagated at the output. So, now your job is done. So, you are propagating the output from here to here. So, now it has reached the primary output. So, test pattern is generated. So, what is this test pattern? This is the test pattern. This is the test pattern. And what is the output? The output is d. So, normal case 1, fault case 0. So, this will actually say that your fault has been propagated to the output and your job is done. That is, you have found out a test pattern, this is the test pattern, and what is expected if the fault is there, you will get the value 0 at the output, if the fault is not there, you will get a 1 at the output. So, you can stop your D algorithm at this point because this fault effect has reached the primary output and the input values whatever you have, whenever you get the value propagated at the primary output, that is your test pattern. But now, had it been the case that there is another inconsistency, for some reason there could have been another inconsistency here for the time being, say it is not in the example, but just assume that even 0x would not have solved your purpose, then we should have been declared that the fault is not testable. Why? Why the fault would have not been testable? The fault would have not been testable because there is no more option available. So, there is no more option available because there was only 2 d frontiers which you have tried, and there was another option of x 0 and 0x at the AND gate number 1, that also you have tried out. So, there is no more option and you have to stop it over here. Okay, so this was actually a detailed discussion about D algorithm using an example. But now you might have observed that D algorithm will never tell you which of the option is better. So, if somebody would have told us, then we could have directly taken gate number 3 as the D frontier in the first case, and instead of using a 0x, that is we could have taken this one as the D frontier in the first case, and instead of using x 0, we could have directly taken a 0x and we have solved the problem. But nobody is there in the D algorithm to tell you which is the better option, you take it first or you take it second. Nobody tells you that. So, that is what is the problem of D algorithm. So, there were some advanced algorithm like PODEM and FAN which actually gives you an idea that that will tell you that it will give you a guide that which is the better D frontier, which is the better option to take, so that the inconsistencies are less and there is less time for backward propagation. That is the basic motivation of the advanced algorithm PODEM and FAN. So, we are not going to go into very details in this course, but just will give a very brief idea what they are. So, that is what I told you, the D algorithm sensitizes, propagates and justifies. But whenever there is a backtrack is there, so D algorithm will never tell you that why is that back, it will tell you why, but it will not tell that what you can learn from that backtrack. Okay. So, D algorithm provides all these steps, but it does not prioritize among the options available. And the reason for inconsistency is not used for future selection of alternatives, that is very important. So, whenever D algorithm fails, it will never tell you that what are the why, it will never tell or it will never learn that this is the case that there was an inconsistency. So, better I use this learning mechanism in my choice of the next option. Okay. Also, it will not set a priority that gate number 2 is the first priority for deep frontier propagation, this option is the first priority, this option is the second priority. The algorithm is just selecting randomly, and that is why this is a problem. So, this advanced algorithm like PODEM and FAN, so what they do is that they sometimes they give you a lot of heuristic choices to find out that which is a better alternative. Like sometimes they can say that they take the shortest path from the fault side to the primary output. They say that if there are 3 or n number of D frontiers available, you take which path? You take the path which is the shortest or minimum number of gates involved to the output, you take that path, then that is very good. So, if there is n D frontiers, the one having the shortest path to the primary output can be a choice. Similarly, you can use squab values to find out that which are the easier paths to drive your faults and which are the difficult faults to drive your pass. Like for example, to propagate the fault effect to an OR gate, so one input should be 0, and there can be another option in which you have to propagate the same output by another AND gate. So obviously we know, so let us say that some fault effect has to be propagated through this input of the AND gate. So this has to be 1. Same fault effect can be propagated through an OR gate also, say for a time being. Say this is the fault effect being propagated. So this one you requires a 1 and this one requires a 0 to be propagated. Now by square value you can find out, is it difficult to make this 1 or is it more difficult to make this 0. So whichever is more difficult, you avoid that and you take this that gate whichever is easier to control. For example, if 0 is easier to control, then take OR gate. If 1 is easier to control, then take this that. So with this type of few randomized, so this type of few heuristics, what actually advanced algorithms like Mod-09 and FAN do, they will give you priorities, that you take this gate as the first option for your D frontier propagation, you take this choice of singular cover for the justification of the J frontier and so forth. And if there is an inconsistency, it will learn and then again reset the priorities. So this is how the advanced fault algorithms have been developed, and D-algorithm was the first algorithm in this arena. So D-algorithm has its own charm, and still everybody has to learn D-algorithm, what we have seen in these 2 lectures, because that is the building point of all, what you can say is the building point of all ATPG algorithms, or the backbone of all ATPG algorithms. And whatever ATPG algorithms like Mod-09, FAN and advances had been are made on the background or on the what you can call the base of D-algorithm. So before we close, we will just see very 2 quick questions. So use D-algorithm to show that the fault the circuit below is untestable. Okay. So now how do you find out circuit is untestable? So you have to find out an inconsistency and then you have to find out that there is no more option available, correct. So in this case, so everywhere you have put x, you can see. So this is stuck at 0, you have to apply a 1, so value of D will be there. So now what is the value of, what is the J frontier, sorry D frontier over here? This will be the D frontier, because this is the only gate your fault effect can be propagated, and we know that the output is a 1. So and this are the 2 inputs of the AND gates are XX, so this one will become your J frontier. So 1 is J frontier, 2 is D frontier. Correct. So now what you have done, so so now you require a 1 over here. So by backward implication of the J frontier, so you can say that A is 1, D is 1. Again by backward implication of this fan out, so you require a 1 over here. That is the thing. And now if you want to propagate this to the output, so this is D for the OR gate, this one will also be a D. So once you propagate this value here, so there is no more D frontier, so that is very simple. Now again this you can think that 2 can be a part of the J frontier, because you know the output is D, okay, and you require some value here to propagate this value. So this is obviously a 0, because we know that 0 is required to propagate the fault effect to an OR gate. But now you see, if it is a 0, so there will be an inconsistency over here, and now you have to, so there is an inconsistency, you have to stop. But you have to find out very, you have to observe very carefully here that there was no choice at any point, because from here there was a unique D drive, that is unique D drive. Okay, so this is the unique D drive, so there was no option. And in no point of time, while what you call backward implication of the J frontier, we had any option like x0 or 0x or 10 or 1x. Everything was fixed. So there is no more option. So you have to say nothing, but you have to say that your fault propagation is stopped. So that is the only option you can say, that your fault, so the only option you have to say that your fault is untestable, because there were no more options, so no more backtracks. Okay, so that is one example by the question we have illustrated, that when your D algorithm says that it has failed to detect a fault. Next example, last question actually. So explain using an example why singular cover is used for implication and not fixed value of signals, that is x0, 0x. Why do you want to keep so many x's in our circuit in D algorithm and not use any other stuff? What do you mean by any other stuff, like 1 1? Because output of a OR gate you could have used 1 in the OR gate, you could have used x1 or 1x, or you could have also used 1 1. But why we are not using 1 1, or why we are not fixing most of the values in the circuit? To keep flexibility. So this is illustrated using an example. Say for example, this is your circuit, so you have to put a D over here. So now the output, so this is a D, so next step is this one, so it is a unique D drive. So obviously so this one will become your D frontier, the effect has to be propagated, so you have to propagate the effect to this one, so it is a D over here. Correct? So if you have to get a D over here, then what do you require over here? You require a answer of a 0. Anyway, so this is the case. So first this is D propagation. So let us see the step 2. So this D is the D frontier, the effect has to be propagated, but also at the same time you have to also get the value of a 0 over here. So again these 2 values has to be fixed. Okay. So, now the value has to be fixed means the value of the output of the AND gate is to be 0, that has to be derived by backward propagation. So, you can say that this gate is a part of a J frontier. So, this value has to be fixed. So, now what is this value has to be fixed is, so AND gate output 0 you can take 0 0, 0 x or x 0. So, in this case the guy has taken x 0, okay, and you can see that successfully he will solve the problem that already we have seen. So, it is x 0. So, this is the case, right. So, now you can so it is the D is there. So, we know that we propagate the value of D from this D frontier. So, you require a 0 over here. So, it was x, correct. So, you could have put a x. So, it was x. So, immediately you cut this x. Sorry, it was x. So, immediately what you could have done, so this x is there. So, x you convert, sorry, it was x. So, you convert the x to 0 and your job is done. So, that is your problem is solved. But now, had this person been selected some hard coded values, like for the AND gate output to be 0, it can be 0 0 0 1 or 1 0. So, instead of using x 0, you could have used any one of this. So, for the there is hard coding of somewhere. So, let the person have used 1 0. Still your problem is solved because you require a 0 over here, and if I put a 1 0 in this, your problem is done. So, now you have propagated the value, fine. So, D has been propagated, but this is 1 because he has not used this x 0 or 0 x concept, that is keeping flexibility, that he has hard coded. So, it was successful here, it was successful here, but now you see it was a 1 because he has not used x. So, there would be an inconsistency because you require a 0 at this, but it is a 1, and you will declare that there is a big problem over here, and that is the circuit fault cannot be tested. Again you have to try out with the other option like 0 1 or 0 0, all these options you have to try out. But by keeping an x, all these problems are gone. That is what was the emphasis, that D algorithm you have to keep more number of x's to keep your to keep your options open. That is, you have to defer your inconsistency as much as possible. So, that was about the lecture on ATPG of combinational circuits using D algorithm. In the next section or in the next lectures from the next class, we will study in details about sequential circuit, because till now all our discussions were limited on combinational circuits. So, with this we close. Thank you.